Welcome to Augment Yourself, a show where we explore the hottest AI topics, techniques, and tools hands-on. My name is Jan Stichitz, Director of Data Science at Shelf, and the topic of the day is Garbage In, Garbage Out, Retrieval Augmented Generation Edition. Let's jump right into it. Garbage in, garbage out. What is it? What does it mean? It is a concept where poor quality inputs lead to poor quality outputs. And it is referred to very often in the context of generative AI, where poor quality data leads to poor quality generations from large language models. What I want to focus on today, however, is retrieval augmented generation. So it is a technique allowing teams to ground large language models in their knowledge bases. And garbage in, garbage out is especially true for RAG. As poor quality input data, poor quality knowledge bases, not properly structured information will lead to poor quality answers from RAG systems. Now, this is the third RAG video we are doing on this channel, so I invite you to check out the previous two. First one is generally covering RAG. How does it work? Why is it driving adoption in the enterprises? And the second one is covering how longer context windows within large language models are impacting retrieval augmented generation systems. But today, let's focus on garbage in, garbage out. And a very frequent question is, it makes sense, it sounds smart, but what does it actually mean? What are some of the examples of poor quality data leading to poor quality responses in retrieval augmented generation? I want to approach this first looking at a retrieval augmented generation pipeline, just to refresh our memories, how does information flow within RAG, and then look at 7 concrete specific examples of poor quality content or content issues leading to poor answers. And throughout the video, I will refer at times to a paper titled 7 Failure Points when Engineering Retrieval Augmented Generation Systems. And it is a research paper published at the start of this year, and it shows what is the impact of poor quality content, poor quality information on retrieval augmented generation systems. First, let's look at RAG, a common RAG pipeline. And this is something we covered in depth in our first RAG video on this channel. But looking at the pipeline, we have a user on one side presenting questions, queries to the system. The application then sends this query to the retrieval system. Retrieval system tries to find relevant content pieces, relevant content sections, return those content sections as context. This context is then injected into a prompt for the LLM, which instructs the LLM generate an answer, provide an answer to the question, to the query, but only using the information provided in the context. And then an LLM responds, and this answer is then presented to the user. Now let's look at 7 specific examples of garbage in, garbage out within RAG. So these are the 7 information extraction issues: poor chunking, irrelevant information, data inaccuracies, hard to deal with formats, missing content, and poor queries. And I will show concrete examples. How do these data issues impact retrieval augmented generation system, and where does our system break because of poor quality content, because of garbage in? Let's start with information extraction issues. So the first step of preparing data for RAG is extracting valuable information from our raw data, from our raw content. And now, one core piece of the RAG pipeline is the retrieval system and vector databases. Those expect our content information to be structured in a given way. And now the structure is not the same as the raw content. So we need to take steps to first extract information and then properly structure it. So on the left, I have an example of a PDF. It is a research paper titled "Attention is All You Need." It is really a paper that started the whole generative AI revolution. And we can very quickly see what are some of the hard to deal with elements on this page when we are extracting relevant information for our RAG system. For a human, it might be easy, right? I have the title, I will need the title. Authors, I will need the authors, abstract, footnotes, and then some information on the left. And we can very quickly segment the page into different objects. It is not so easy for automated systems. So covering some of the elements which could lead to issues, side-by-side elements. How do we process this information? Symbols are present on this page. Do we want to keep the symbols or do we not want to keep the symbols? Orientation. a lot of documents are visually structured so that humans can very quickly understand the information that is visible on the page. But this visual structure is actually very hard to process automatically and extract those relevant pieces of content from our page. So here we have vertical text. Do we want to keep that text? How will this text get processed when our automated text parser is covering this page and extracting relevant pieces? Footnotes. Again, they're present in the content, and for a human, very easy to distinguish. This is a footnote. I might not want to include this in the main contents of the page, but as our automatic solution goes over it, it cannot automatically distinguish between all of the elements. So someone who is building the system, this information extraction system, needs to be aware of all of those issues and needs to make a decision. Do we want to keep those? Do we want to keep those elements within our content, or do we want to take additional steps to get rid of those elements? And the first thing is being able to identify those elements, and that is very often an issue. Continuing with poor chunking. So chunking, again, is the second step. After we have extracted information from our documents, we need to chunk this information into smaller pieces which are then saved in our vector database, and for which we generate embeddings, so vectorized representation of text or vectorized representation of meaning. Now, chunking, again, it's not an easy task. If we look at the same page as an example, again, for a human, very easy. What are some of the different elements? Authors, abstract, footnotes, title. For automated systems, it is not so easy to distinguish between those elements. And what I have here is an example. I used an available open source content chunker, and I just ran my page through the algorithm. And what you can see is the example of sections that are produced by this algorithm. And this algorithm, the main input is section size, so the amount of text present in each section. And these are the orange vertical lines indicate where our splitter would chunk content into smaller pieces. And our first chunk, it covers the title, or it contains the title, it contains all the authors, and it contains one sentence from our abstract. And then the second one kind of breaks our abstract in two, and then the third one contains a little bit of the abstract and a little bit of the footnotes. Now, we can very quickly see that that is not ideal, because our system will, for each query, trying to find relevant content sections. And if our content sections are not, let's say, meaningful, if our content is not properly chunked, we have sections that contain information from something or from pieces that should really be apart, right? So in this case, I would probably want authors in one section. I would want the whole abstract again as a standalone section, and then footnotes again a standalone section. This is not something that happens, and it is not very easy to get to an automated system that is able to distinguish between all of those elements and then chunk content where it should be chunked. So chunking is a very important step of retrieval information, and poor chunking will directly lead to garbage in and struggles with our information retrieval system, and also struggles with LLMs when they need to use this content, when they need to use these sections to generate answers. Third issue, irrelevant information, noise. And again, I go back to our example. So we have that vertical text on the left, we have our footnotes, and even footnotes are split into two different parts, two different sections. Is this information that we want in our knowledge base or not? So this is a question that someone who's developing the system needs to answer, or someone who knows the use case needs to answer. But what a challenge is distinguishing automatically. Again, we have an automated system. Usually these knowledge bases are vast. Now our automated system needs to distinguish between those elements, and it is not always that easy, right? What is this part of the main content? Is this perhaps a footnote? Is this a text that should not really be present in our knowledge base? And not being able to distinguish between those elements and not being able to filter out some of those elements will lead to retrieval inefficiencies. We are now vectorizing content that really should not be present in a vector database. Retrieval accuracy, so when our semantic search will be working, or hybrid search will be working, looking for relevant content sections, unnecessary information can be treated as noise. And then also context noise and answer relevancy. This has to do with this perhaps irrelevant information being presented to a large language model when we are requesting it to answer questions. And here is where I want to refer to that paper mentioned, 7 RAG failure points. Noise is one of big issues. So they analyzed poor quality answers, and noise was one of the biggest contributing factors to large language models struggling to provide good answers using the context. Next one, data inaccuracies. Now, an assumption we see made very frequently is our raw knowledge base or our content is good, is perfectly accurate. All the information in there is relevant and accurate on a given date. But we see that that is simply not the case in the majority of examples. And here I have 3 different data inaccuracies or 3 different examples. Number 1, outdated information. So an example on the left, the Milwaukee Bucks win the NBA championship. Now this was true, but it was true in 2021. And if, let's say, a user asked our bot a question, who is the current NBA champion, looking at the semantics, this section could very well be retrieved as relevant for that query, and our bot would be confused. So Milwaukee Bucks win the NBA championship, and it could come to a conclusion, yeah, they are the current NBA champion. Second example, conflicting information, and I will give a very simple example. Let's say a product price does change all the time, and let's say someone does not delete the previous price, right? And now this price has been updated, but there's 2 different information present for the same question, and our bot again would struggle. Which is the more relevant one? Which is currently accurate one? How to distinguish between those? So conflicting information present in the context window will make it very hard for an LLM to provide the correct answer. And again, 7 RAG failure points. This is one of the key issues again with large language models struggling to provide good answers. And then the last example here is factual inaccuracy. So this is information that is simply not correct. So Yao Ming is the tallest player to ever play in the NBA. It is not true, but if this is the information present in our knowledge base, large language models will not automatically just verify all the knowledge, but they will rather surface this information to the user, and that could lead to poor, inaccurate answers. Garbage in, example number 5, hard to deal with formats. So again, a lot of the content we are using in retrieval augmented generation was put together with the intention, with the purpose of humans looking at that information and that knowledge and then quickly gaining insights from it. And elements such as tables, images are very good. Humans are very, very quick we are very able to process this information quickly. But for an LLM, it might not be the same. So here I have an example of a table, and I have an example of an image and evacuation plan. And I imagine a large language model is asked a question, what is the best path to exit the building in case of a fire? And it needs to understand the information present in that image. Now, this is not very easy. This is a hard to deal format, and what we must do, what developers need to do building such systems, they need to take additional steps to process this information or structure this information in a way that a large language model will be able to use it when generating answer. Now, multimodal models coming up make that a little bit easier, but still when processing such information, big tables, big sheets, we need to take additional steps to correctly and properly structure and store this information in our system. Next one, missing content. This is actually the number 1 issue reported in the mentioned research paper, knowledge coverage. Is our knowledge base actually covering all the questions that the user might ask? Here's an example. If a user presents a question and our retrieval system fails to find relevant knowledge articles, it will fail to return relevant context, which then an LLM would use to provide an answer. And what will happen is our system will have to return a message: we were unable to find relevant information for your question. And again, this can lead to dissatisfaction from the user who is using the system. So as we are building such systems, designing such systems, this is something to be aware of. What is our knowledge coverage, and does our knowledge base actually contain all the information necessary to address user questions or user queries? And our last example for garbage in within RAG applications is poor queries. So user questions can also be considered as information that is flowing into our system. And users are notoriously bad at providing or asking good questions. Now, what does a good question mean? So if we look at our retrieval system will rely on semantics or keywords to find relevant pieces of knowledge, relevant content sections. Now, if our question is, example here, stuff about dogs and maybe cats too. It's a question that is not specific. It mentions dogs, it mentions cats. Our retrieval system, as well as the large language model, will struggle to provide a good answer, relevant answer for that question. And this is another thing that system builders or people developing retrieval augmented generation systems need to be aware of, that queries coming in might not always be specific enough, might be too broad, and might not allow the retrieval system to find relevant pieces of section. So there we can take steps to maybe augment the query or ask a clarifying question if the query is not specific enough. But core queries is another example of garbage in flowing into our RAG system. This is it for today's Augment Yourself. We covered 7 concrete examples of garbage in, garbage out within retrieval augmented generation systems: information extraction, issues, poor chunking, irrelevant information or noise, data inaccuracies, hard to deal with formats, missing content, and poor queries. So those are 7 things, 7 examples to be aware of when we are building retrieval augmented generation systems. And our system needs to handle those examples. So we need to take steps to handle, control garbage in, and ensure that data flowing into our RAG system is accurate, relevant, free of noise, and trusted. Only by doing this, we can expect good, reliable answers provided from our retrieval augmented generation system. Thank you for watching, and until next time.